So, welcome to day 3 of the Working Party on Crystallization seminar. As those of you who've joined the previous sessions will know, I am not actually Marco Mazzotti, and my name is Brian Glennon, and I have the honor of chairing this session today. One of my jobs is actually to introduce myself, so I will keep that fairly short. So before I start and introduce our speakers, I would just like to give some background on the Working Party. The Working Party, getting the slides to work here. So the Working Party of the European Federation of Chemical Engineering is almost 70 years old, and it has a charter to promote cooperation and advancement of chemical engineering in Europe. The Working Party on Crystallization is part of the Working Party structure of the EFCE, and it promotes crystallization science and practice through its activities and its events. Its major event is the ISIC series of conferences, the Industrial Symposium on Industrial Crystallization, which are in general held every 3 years, except if there's a global pandemic. So as those of you who are aware, the scheduled ISIC 21 conference has been rescheduled from this year until next, and we'll have more details on the next ISIC conference at the end of the meeting. So there's an amount of information available on both the European Federation and on the Working Party, and some of the links are provided here. Before I introduce the keynote speaker, I just would like to point out that this meeting has obviously a variety of presenters, and the views they express are the views of the individuals, not of the EFCE, the Working Party, or of their institutions that they represent. In addition to the ISIC conferences, one of the other important activities of the Working Party is to award an excellence award in crystallization, and the award is generally coincides with the ISIC conferences and is announced at the ISIC conferences. Because ISIC 20 was postponed, it was decided to continue to have the award every 3 years. So we are going to make an announcement today about the latest recipient of the EFCE Excellence Award in Crystallization. And I'm going to call on the chair of the adjudicating panel, Dr. Rob Gertman, from the Crystallization Technology Unit in Janssen in Belgium, to announce the winner.
Thank you very much, Brian, for the introduction. And indeed, as indicated, one of the activities of the Working Party on Crystallization is indeed also recognizing talented young scientists for their work. Although ISIC, as indicated this year, due to the pandemic, has moved a year, we all in the Working Party felt it very, very important that we still would continue with our 3-year cycle, because science doesn't stop. We need to recognize every 3 years the best PhD students and best thesis in this field. Before announcing the winner, I would also like to thank the other members of the panels, Brian and Professor Daniele Marchisio, for their work in going through the applications and the works. Although I must say, for me, it's never a burden to have a look at good science. And we had very good candidates this year. Especially, I want to mention also, we had a strong runner-up. But fortunately, our deliberations were fairly short, because we were unanimous in assigning the winner. And the winner is, could you please advance the slide? Ryan, thank you. Dr. Ashwin Kumar Rajagopalan, who is, by the way, also behind the screens at the moment at work, making this session possible. So it will be a surprise to him too. The reason why we felt he is the best candidate is that he really worked both in a fundamental area, but also at the application. So he worked on a dual camera setup for having a three-dimensional framework for particle size and shape. He also, together, of course, with other people in the lab, developed an instrument for it. But he didn't stop there. He also coupled that to an actual crystallization setup, including a wet mill, and demonstrated also its application in process control. So in essence, he spent the whole span from fundamental area to actual application in a process, and that's all what the work in the crystallization area is all about, understanding your fundamentals, but also getting them applied. So in that sense, a heartfelt congratulations to Ashwin for deservedly winning this prize. Due to the movement of Isaac, or the postponement next year, he won't be able to present his work now, but I really want to call upon all the audience to come to Isaac next year and seeing him presenting his work. Thank you.
Thank you, Rob. And congratulations, Ashwin. I'm conscious that Ashwin is in control of the session with Lucas, so I hope he can still remember to press all the right buttons. But again, well done and congratulations. So now we have the start of the session on industrial applications, and we've 4 very good speakers today. In a change to the original program, the keynote speaker for this session on industrial applications is Dr. Chris Burcham. And I started to work out how long I've known Chris, but then I decided I wasn't especially kind to either of us. Suffice to say that over the last 20 years, Chris has been one of the most productive and innovative leaders in industrial crystallization in the pharmaceutical industry, and in particular in the area of continuous manufacturing. So he's going to share some thoughts today and presentations on the development of a continuous crystallization system with periodic wet milling. So I'll hand over the reins to Chris.
Brian, thank you for that very kind introduction. And it has been 15 years that we've worked together, so it's really quite impressive. So it's been a fun ride. Let me get my screen up. Okay, so hopefully everyone has seen the title slide and not the presenter view. And let me go ahead and get going. All right, so again, thank you for that kind introduction, and I really want to thank the Working Party for the invitation to speak to you today. For those that were hoping for Jean-Paul, I apologize. I'm not going to be able to be anywhere close to his level of presentation skills, but nonetheless, I do hope that you'll find that what I'm talking about today to be interesting and hopefully motivating. Today I'll talk about, as Brian said, utilization of inline wet milling for particle size control during a continuous crystallization. I will say when we started this work, it seemed like it was such an easy concept. And then as I will point out, it turned out to have some challenges that were pretty exciting to overcome. This project that I will discuss is a very real project. And you can tell by the large number of collaborators on this work that there was a lot going on. So this was part of a multi-step, fully continuous drug substance process, which involved, I believe, 3 different chemical transformations, a couple of different separations, liquid-liquid extraction, distillation, concentration, you name it. And then at the tail end was the crystallization and isolation of the API. I want to call out one particular colleague in particular, and that's Václav Svoboda. Václav really should be giving this talk today. He did the lion's share of the experimental work that I'll be discussing. So appreciate and acknowledge all the efforts that he provided to this work. And then my collaborators at PSE who helped to with the modeling aspects that I will discuss. So.
Again, there's a lot more questions, but I'm afraid we do have to call halt. But again, just thank you again. That's been a fascinating talk, and I guess the number of questions indicate the interest in the audience. But thanks very much for joining us.
Thanks, Brian. Thanks, everyone.
So if you can stop sharing your screen, if that's okay, and I'm going to ask our next speaker, Alison Lewis, who has been a great supporter of ISIC. So we're delighted that Alison can join us, albeit virtually. And I'll hand over to Alison now to deliver a talk on freeze-based crystallization methods.
Thank you very much for the introduction, and thank you for the honor and the pleasure of presenting here. As you said, the talk is about treatment of brines from power generation using eutectic freeze crystallization. And I'd like to start by thanking my co-authors, Jamitius Chivavava and Abdul Malik Lottering, who carried out the work. So this work was carried out at the University of Cape Town in the chemical engineering department. And I'd like to start my talk by taking you back to 2011. And this is a headline in National Geographic, which says, "Could seawater solve the freshwater crisis?" In other words, desalination is the great technology of the future. And then this, in 2019, desalination plants produce more waste brine than thought. And here we have a massive desalination installation at Dubai, producing massive amounts of brine. If you look at various flow sheets that are available on the web that show how reverse osmosis desalination works, you'll see something like this. Here's the seawater coming in to be treated in the RO system, the post-treatment, and here's the fresh water produced. But the chemical engineers will see that there's something missing here, and that is the waste stream. What it should actually look like is the same process. So you treat either ocean water or mine water to desalinate it through your reverse osmosis process. But here you will produce a leftover high salinity brine. And the question is what to do with that brine. So first of all, let me show you in South Africa an example of industries that generate brines. And you'll see on this graph, I've got on the x-axis the industries, and the bars show either the total effluent of brine, with the red bar showing the effluent excluding that discharge to the marine environment. So for example, you can see that fish processing produces a huge amount of brine, but it's all discharged to the sea. So we're looking at the red bars to look at the inland disposal areas. And here we have paper, pulp, and wood, petroleum, mines, and power generation being our biggest generators of brine. Most of those brines are put into brine ponds, which are expensive, unsustainable, and in fact, there's new legislation just come out in August of this year, which says that it's not acceptable to build brine ponds anymore. So the industry is looking for solutions to treat these brines. Here are some options of desalination technology. So you'll see there's a huge menu here. But one of the issues is if you look at that menu of options and you rank them according to the maximum feed salinities, you'll see that it's only multistage flash that can treat up to 70,000 ppm. Reverse osmosis, which is the workhorse of the industry, treats up to 45,000 ppm. And after that, you run out of treatment options. So our proposal is to take this leftover high salinity brine and put it through a eutectic freeze crystallization process to produce ice and salt. The ice, of course, is the water that you're recovering. And because of the density difference, ice will float and salt will sink. And you can have a solid-solid separation process. So how this works in practice is, here's the crystallizer filled up with brine. You drop the temperature to below 0 degrees because you're having a freezing point depression in the saline water. Just below 0, the ice will start to form. At some lower temperature, your salt will start to form. Because of the density difference, the ice will float, the salt will sink, and you can recover ice and salt. Theoretically, you can do this sequentially. So in the first crystallizer, you feed the brine in, seed with the salt of your preference, recover, for example, calcium sulfate and ice, and then feed the remaining brine from that stage into a second stage where you seed with a different salt. So for example, sodium sulfate, recover the sodium sulfate and the ice. And this has got the advantage of being able to recover useful salts, such as sodium sulfate, also calcium sulfate or gypsum. And this picture shows a housing project using gypsum that was recovered from mine water. Another advantage of the eutectic freeze process is that ice floats. Impurities are excluded from the ice crystallization due to the small size of the ice molecule. Corrosion at the low temperatures is minimized. Working at low temperatures is also safer. Equipment design for liquid solid systems is simpler than that for liquid gas. There's no added chemicals. And the energy requirements, the difference between evaporation, where the heat of vaporization is 2,300 kilojoules per kilogram, and in freezing, where the heat of fusion is 334 kilojoules per kilogram. So there's 1/6 of a difference there, as well as the fact that the heat of fusion is released when you crystallize the ice. So this makes potentially the carbon footprint of this process much, much smaller than that of evaporation. So I'm going to present a case study that we carried out in our labs at the University of Cape Town. And this was a brine from fluid gas desulfurization. And you'll see here, it's a multi-component brine with a large concentration of magnesium, but also sodium and calcium, and then large concentrations of sulfate and chloride, but also bromide and fluoride. So the first thing we did was carry out a thermodynamic modeling exercise. We used a program called OLI Stream Analyzer, which uses a mixed solvent electrolyte framework. And on this graph, you can see the x-axis shows you how we dropped the temperature from 5 degrees all the way down to -25. And on the y-axis, we have the grams per liter of either the ice or salt produced. So the first series is ice, and you can see here that the ice nucleates below 0 degrees C, and at the maximum here, we're recovering almost 900 grams of ice per liter of water. We also produce calcium sulfate or gypsum, magnesium sulfate, which nucleates at quite a low temperature of -10. We're also producing magnesium fluoride in low quantities and silica dioxide. So if we look at the major salts and their nucleation temperatures, we have both ice and calcium sulfate nucleating at -1.5 degrees, followed by magnesium fluoride at -2 and magnesium sulfate dodecahydrate at -10. So part of the modeling exercise tells us that we should be operating our process for maximum recovery at about -20 degrees. So if we translate this into a process design, we would have significant amounts of the water recovered as ice, and our prediction at -20 is 87% of the feed. We'd be producing a mixed salt, the majority of which would be magnesium sulfate at 50 grams per liter. We are, however, also producing a couple of scaling salts, gypsum and silica, and we're predicting the maximum recovery of the products at -20 degrees. If we look at the experimental validation, which was the next part of our process, what we discovered was that our ice recovery was only 60% of the feed, which is still very reasonable, but we only recovered one salt, and that was the calcium sulfate. And that was only recovered at -3.17 degrees C. So that is pretty different to the modeling that we predicted. We also showed that operating a single stage at -20 degrees is not practical for multiple reasons, and I'll go into those shortly. But this also does show the importance of not only modeling, but validating the model, as well as the importance of kinetics. And I think this also echoes the earlier speaker who was speaking about exactly this: modeling, validation, the importance of kinetics. And I suppose the next part was something that looks easy in theory is sometimes more challenging in practice, but I'll get onto that in a moment. So the products we produced were ice and our calcium sulfate dihydrate salt. And in practice, we ended up with a multi-stage process design, partly because ice management is just not possible in a single stage. You're producing 60% of your feed in the form of ice, and it's impossible to manage it in a single crystallizer. So we ended up splitting it into 4 stages in order to effect the ice removal. But the other really important for doing the multi-stage process is that it allowed us to have a meaningful temperature difference between each step. Usually, if you form all the ice in one step, with the heat of fusion release, it's really difficult to get the temperature down and thus affect the brine concentration that's necessary in order to start producing the salt. So even after all this, the 4 stages, each one at a meaningfully different temperature, we still only produced 1 salt, and that was the gypsum at -3.17 degrees. So our conclusions of this stage of the project, this is an implementation of multi-stage EFC. Up to now, it's only been theoretically possible, and all applications have been single stage. We've shown that significant quantities of ice need to be crystallized before achieving freezing point depression and solution concentration. As I've said, it was necessary to use a multi-stage process to get this meaningful temperature difference. And understanding this need for multi-stages is absolutely key in our view for design purposes. We also showed that salt crystallization did not obey the predictions. Gypsum only crystallized at a much lower temperature than the predicted one. Magnesium fluoride did not crystallize at all. And once again, this is important design questions around the kinetics of crystallization of these salts at low temperatures. So since this is a session on industrial applications, and the previous speaker spoke extensively about the industrial application, and in particular, how something starts off looking easy but is challenging. These are some examples of the industrial application of eutectic freeze crystallization. We do have a pilot scale plant of 2,000 liters per day built by our power provider called Eskom. And this pilot plant had serious problems with scaling salts. They weren't taken into account correctly in the design, and so the pilot plant is currently being redesigned. This is a 500,000 liter per day plant built at Optimum Colliery, and it was commissioned straight from the lab scale, which I think was one of the many reasons that there were issues with it. There were issues with not only scaling, but also scraper design. And so this is now also closed for redesign. And this other 28,000 liter per day plant at Tweefontein is currently being redesigned to accommodate scaling salts. So I wish I did have a final slide showing you the successful design, but that'll probably have to wait for the next ISIC. So the lessons we have in Scale Up so far is that modeling has huge value in identifying the right applications or place for eutectic freeze crystallization, and that it's really important to integrate it with existing technologies like reverse osmosis. So in other words, thinking systems and processes instead of just technologies. And one thing that is common between all 3 of those large-scale plants is that seemingly small quantities of sparingly soluble compounds can be the difference between success and failure. Separation of ice and salt is very simple in theory and much more complex in practice. And full-scale design often raises new questions that are not obvious at lab scale. And lastly, good partnerships with industry are absolutely vital. So thank you very much, and I'm very happy to take questions.
Thank you, Alison. That was fascinating. You mentioned it during your talk. Maybe you might comment a little bit more on the difference between the thermodynamic and the kinetic modeling. And so can you just clarify, in the modeling where you were looking at predicted nucleation temperatures, was that based on just a thermodynamic view of the system, or were there some kinetics built into that?
Yeah, so that is a purely thermodynamic model. Mm-hmm. And what we found is that we've modeled probably tens of different systems, ranging from seawater brines to mining brines to agricultural brines to fracking brines, all sorts of different brines. And on the whole, the thermodynamic predictions have been pretty accurate. Mm-hmm. But for some systems, especially multi-component systems and systems with these scaling salts, we find that we have to incorporate the kinetic factor.
And any thoughts on how to generate that kinetic data?
What we probably do is go into the lab and start looking at how it plays out in practice. I'm not thinking that it would be, maybe it's, I hadn't thought about incorporating kinetic models into our, into our eutectic freeze models. So yeah, maybe that is something we should think about doing.
Okay. And what was also noticeable was in the multi-stage systems that you showed, the temperatures were very precisely quoted, the second place of decimals. Is that the level of control that you think is actually needed?
Yes, so the point of that slide, and it's not an obvious point, is that it's actually really, really difficult to get the temperature down to the required temperature, because you're producing ice like crazy, and all the ice that you're producing is busy heating your system up. So you have to have a really, really good heat transfer set up in order to be able to get the temperature to reduce in order to produce the ice and thus to concentrate the solution. So yes, those are hard-won decimal places.
But it sounds then that may present some scale-up challenges, particularly on the scale of some of the systems you were looking at, and that what might be required for this level of treatment.
Yeah. So at the moment, as I said, the biggest issue on the scale-up is the scaling salts themselves. And as is well known in chemical engineering, when you scale up, you're going to get a loss of efficiency of your heat transfer, not a loss of efficiency, but your surface area to volume ratio will change. And therefore, we have to think about incorporating more heat transfer surface area into the larger scale installations.
And can I ask, obviously in the previous talk, for example, from Chris Burcham, he was dealing with an API feed stream where the inputs were probably pretty predictable. In the sort of feed streams that you're looking at here, how variable might the input concentrations be? And will that have an impact on the design?
Yeah. So I think the one thing we do benefit from is the fact that at the moment, most of our feed streams come from brine ponds. So there's a huge buffer tank ahead of the installation. Okay. So I would say at the moment, there isn't much difference. But obviously, as we start treating streams straight off the plant, there will be more variability.
And any idea of what the implication of that might be? I mean, you mentioned that small, even trace amounts can have an impact. Is that likely to make the industrialization of it more complex?
I don't think it's going to change the fundamental design that much. Okay. The design is still going to be a challenge around heat transfer and preventing of scaling. And I think once we've got that right, then I don't think that variation or variability in the feed is going to play that much of a role.
Very good. Again, Alison, I'm conscious of time, but that's been fascinating, and we look forward to the update at next ISIC.
Thank you very much. I hope to be able to give that. Thank you.
Thank you, Alison. So our next speaker is Ruben De Keyser from Janssen Pharmaceuticals in Beerse, and Ruben is going to share some work that they've done on utilizing PAT feedback to provide better control or more precise control for an industrial process. So Ruben, I'll hand it over to you.
Hi, thank you, Brian. Thank you for being on the ISIC 20 webinar. And I'll give you a small story on the Janssen problem we had a few years ago. So once upon a time, we had an API which was a multi-ton drug, which was a hemihydrate, and it was already commercialized. But then, yeah, the earth shook and a big problem arose. So the nightmare of all pharmaceutical companies happened, and after commercialization, a new polymorph showed up. This polymorph, pseudopolymorph in this case, was even more stable. The problem was that it was already commercialized. So the constraints for a new process or for the process at this moment was that the product is a hemihydrate. The PSD is fixed in a very narrow range. Because it's a multi-ton drug, there's a big pressure on the cost of goods. And of course, the timeline was by yesterday. Now, how did we tackle this approach? How did we tackle this problem? First, we had to know where we were, in fact. We didn't know anything about the monohydrate, so the phase diagram was mapped. We tried to stabilize the process that we had in our production plant at that moment. And then in the meanwhile, we did some exploration routes to how can we have form control and PSD tuning in the same time. Then we found out that PAT was the way to go. And in the end, I'll show you the final process overview. So now, at first, something is. So a little bit of background is that, yeah, it's the hemihydrate, and the process solvent is isopropyl acetate, water. For those who do not know isopropyl acetate, it's already separating water after about 1.8 weight% of water. So the water activity is in fact very high. So the a little bit more water gives already a lot higher water activity. Therefore, the hemihydrate is less stable. In the initial investigation, we needed to tackle the needle-like crystals with inline crystal engineering to end up with a rod-like crystals. So we had to face the form problem, but we also had to face the particle size problems. It wanted to grow into needles. Then it was already a process which had a very high throughput and a good yield. So we all need to match this. The old process I'll show you here is in function temperature and function of time, but also for the phase diagram and part, we also take in account temperature and function of water content in the mother liquor. If we seed our solution, the crystals will start to grow. While they grow, in fact, they take up water from the mother liquor. Because it's a hemihydrate, it will consume water to build crystals, in fact. If we then cool further, it goes into needle-like crystals. Then we will mill those needle-like crystals down into smaller bits. These smaller bits are dissolved in Ostwald, so the whole reactor, in fact. So the crystals are in the reactor. It are high shear milled and recirculated into the reactor vessel. then the whole reactor is heated, and then the smalls dissolve, and then we repeat this twice to gain, instead of needle-like, we get rod-like crystals. In the temperature over water content graph, you can also see how it in fact goes. So during aging, a lot of water is already incorporated, high shear milling, Ostwald, and cool down to isolation. And as far as we knew then, it's completely in the hemihydrate zone. But then the monohydrates appeared. And as you can see, both the crystal engineering step, so the high shear milling, and the isolation are within the monohydrate system, in the monohydrate favored part of the phase diagram, therefore making the process metastable. So it was always luck for us that we could isolate hemihydrate anyway. How did we now stabilize this dynamically unstable process? We tackled especially the formation of the monohydrate. Because we never encountered it in initial polymorph screenings, the nucleation is always very slow. So now, by lowering the water content prior to seeding, we will slow down the kinetics even more. We had to rinse the high shear mill loop during the batch, because there were two high shear mill steps, and in between batches within the same campaign. We had to do, all the operators had gowning procedures, so everybody needed to change. For limiting the business risk of a contaminated batch, we had to clean the centrifuge and dryer every 3 batches, instead of having a campaign of 15 to 20 batches. And this gives a yield loss. Yield loss means money. So that's not really favorable. And then also, it wasn't possible anymore to reprocess a batch, because experimentally we proved that every time we recrystallize it, both the induction and the transformation times of the hemihydrate to the monohydrate decreased significantly. So it wasn't possible to do any reprocess anymore. So now you know our constraints, what we at least have to deliver in our new process, and where we are. So a very small target of hemihydrate. So how did we now tackle it? So the different ways of going to the correct form, and the eventual process you'll see. First, we tested some alternative solvents. As I already mentioned, the water activity in isopropyl acetate water is very high. So therefore, we modeled the water activity in function of weight percent in the water, and then in the mother liquor, and then we took less steep solvents, so where we had a much broader window in water activity. However, this came a lot lower in yield, and the morphology, as you can see, is significantly different. So this wasn't an option to implement this. If we do form control with continuous crystallization, this is also possible. However, this is way too complicated for the current plant, and the control of the water was way too difficult. Therefore, we went to a highly concentrated crystallization and control of the water content. So there was a problem though. It's form control and PSD, but this is what we tackled, as you will see in a short bit. this is the phase diagram. So the hemihydrate is the desired form. As you can see, it's a very narrow at isolation temperature. Therefore, in fact, we did a reversed engineering. We knew that at isolation temperature, we only had 0.10 weight% of water window where the hemihydrate is thermodynamically the most stable. If we have it at isolation temperature, 0.1 weight%, we know that at seat temperature, we also have only 0.1 weight% of water as a window where the hemihydrate will be safe at the end. And this, prior to seeding, our solution is homogeneous. And when our solution is homogeneous, we can use quantitative NIR measurement to adjust our water content and the concentration of the API. So this is where our control of the form comes in fact. So we control the water, the operator gets the number of the water, and only if the water is within the range of 0.1 weight%, the operator can proceed. After the water adjustment has been done, we seed and we cool. The same as in our old system, we know that how many crystals, how much water will be included in the hemihydrate crystals during aging and cooling. When we are at a temperature because now we have needle-like crystals, because now we have to change the morphology. We also implemented a new technology, a new platform for Janssen. So subsequently, high shear milling and a heat exchanger. So an in situ Ostwald effect. So the crystals, the needle-like crystals, go into the high shear mill, and they'll go, before they even come back into the reactor, the fines will already be redissolved. How does this look like in production? So we have the needle-like crystals. They get milled within a high shear mill, and then they go through the shell and tube heat exchanger, and here the suspension will be heated. These crystals, they return into the reactor, and there all the fines are redissolved, and you get a very narrow particle size distribution. So this is where we are now. So we have form control and particle size control. If we would cool then from the high shear mill step to room temperature, we again come into the monohydrate zone. Therefore, we have to go to this place. How did we do that? Very easily, by just simultaneously diluting the system with isopropyl acetate. So the water amount stays the same, but in fact, by diluting the system, you lower the water activity. So technology and PAT for us bridge the gap, because what did we have to do? We had to have a robust crystallization within the hemihydrate, and this is now controlled by NIR. So inline PAT gives the operator the signal whether he can proceed or not. By having the high shear mill and the heat exchanger in combination, we have a fixed. We have a very robust PSD over the batches. So, and within the narrow zone, the stress on cost of goods is met. We have a slightly lower yield, I have to admit, but the batch time is significantly shorter, for 14 versus 8 hours. And it was timely it was timely implemented. We still have the problem or the danger of the monohydrate, but in fact, we bridged the gap with PAT and technology. Thank you for your attention, and I'll be happy to take questions now.
Thank you, Ruben. It's a very interesting example. You mentioned early on that the water content, the range of water content is actually very small. It's less than 2%.
Mm-hmm.
Talk a little bit on just how you, first of all, even constructed the phase diagram. It sounds like you needed to have extremely precise measurements of the water content, and you've this balance between the water of crystallization and the water then in the solvent itself.
Yeah. So we did all these tests. That's why it was the easiest to stay with the current solvent system, isopropyl acetate water, because we took a lot of time to make the competitive slurries within this system.
Mm-hmm.
And so we always used 50% of the, well, 30 of anhydrate, hemihydrate, monohydrate. We then slurried them with a Raman in there, so a Raman probe, inline Raman, to see when it will, when there was no more conversion. And then we took Carl Fisher samples of the mother liquor. So then we could, as long as the three form, well, it depends on which border you are. If you always have monohydrate and hemihydrate at the same, both still present, and the signal of the Raman says there is no more change, and it took a lot of time, then you know that the water content at that moment is actually the phase boundary. So that's how we made it in that was the most successful route to get this phase diagram. So point by point.
Okay, very nice. And in retrospect, have you any learnings from, or on why maybe these new forms hadn't been originally discovered during the earlier development?
What we, our biggest lessons learned is, if we look at product that we had still standing, we couldn't even get it to convert to the monohydrate. So there was trace amounts. We couldn't even find it with HPLC or UPLC, even TLC. There was something in the product that just doesn't want it to crystallize. Mm-hmm. So we got our chemistry better. So now by having the better chemistry, we had less impurities, well, trace impurities, and these, instead of inhibiting the nucleation of the monohydrate, they didn't inhibit it anymore. So now the conversion went faster. So now we redo polymorph screenings when we change our chemistry. So we have different steps in the development. Again, a polymorph screen, or we put it on preparative separation. So I have very, very pure API to start with.
Very good. And a final question. Obviously, your control strategy does require very precise control on the plant. If for any reason you have a deviation from the range that you wish to operate in, can you recover the batch? Can you get back in range and maintain the correct form?
Yes, but that will, you will have to redissolve. Okay. So, but there's no problem if you start, in fact, I didn't tell that, but you start with monohydrate as your input, and by default, you start with too much water in the system. So you have to reflux off water. And if you reflux this off, if it's not enough, you can just go back into reflux. Or if it's too low, the water, we can just add water. So in fact, we would always stop prior to seeding. So that is in fact our control strategy. So prior to seeding, but the NIR also picks up monohydrate or monohydrate, hemihydrate once it's crystallized. So if we're at isolation temperature and we see that there's for some reason water in the system, more water than we expect by any cause, by any problem, we can always redissolve and the batch is not lost.
Very good, very good. Ruben, thanks for that. Again, we're just caught with time without a fascinating case study. So thank you again for that.
Thank you for having me.
Okay. So as you're stop sharing your screen,
Yep.
Our final speaker is Joachim Scholl, and Joachim is working with MSD in Switzerland and is going to give another talk on
where's my
applications of PAT. I know it's sometimes hard to find the stop sharing.
Yeah. Yes. No.
There you go. Thank you.
Yes. Sorry.
Thank you, Brine, for this kind of introduction. And I hope I bring up the slides here and switch on the laser pointer. Yes, so my talk will cover, again, PAT today. So I will highlight a couple of examples from MSD on the efficient use of these PAT tools for process development.
Very good. Joachim, thanks for that. I'm conscious that we're approaching 5 o'clock on a Friday afternoon, so I'm definitely not going to run over time. So again, just thank you again for presenting that very good 2 case studies.
Thanks to you. Have a good evening.
So as Joachim is knocking off his screen, let me just call up my slides again. So we've come to the end of our session. As Marco introduced it on the first day, this was in response to the postponement of our planned ISIC 21. I hope you've enjoyed the talk, and I'd like to obviously thank all our speakers, particularly our keynote speakers, Martha Glover on day 1 and Heiko Bryson yesterday, and finally Chris Burcham today, but also to thank all of the other speakers. As Marco had said at the beginning, ISIC 21 has only been postponed, so it has been rescheduled. It will be held next year in Berlin as planned. And for those of you who have never been to Potsdam, it's worth a visit by itself, but the added attraction of ISIC should make it pretty irresistible. The abstract submission system has been reopened because obviously we want to make sure that the talks presented are as up to date and representing the latest research. So we would invite you to visit the website and look at resubmitting work for presentation at the next ISIC. Again, we'll have further information over the coming months, but we do want to flag the abstract system being opened. So again, I'd like to thank you all and thank Ashwin and Luca in particular for managing the technical aspects of it. It's working on my end, so I hope it's been working on all of your screens as well. And we look forward to welcoming you in Berlin on the 30th of August in 2021. Thank you very much.